Hey students, today we will do paper 6 of 2024 May-June variant 3. So let's start it. Question number 1. A sample of rock salt contains sodium chloride, sand and mud. So it means we have a mixture of these things, sodium chloride, sand and mud. Sodium chloride is soluble in water, sand and mud are insoluble in water. A student obtains dry crystals of pure sodium chloride from a lump of rock salt. So, rock salt, which is a mixture of all these three things, a student obtained pure crystals of sodium chloride. So, figure 1.1 shows some of the steps the student uses. First of all, a student grind the rock salt into small pieces. Step 2, add the rock salt to water and heat while stirring with a glass rod. Filter the mixture. So mud and sand will remain on the residue, and in the filtrate we get aqueous sodium chloride, which we can later crystallize. So this a student does to obtain the crystals of sodium chloride. Now let's see what are the questions. Explain why the rock salt is made into smaller pieces. So rock salt is made into smaller pieces to speed up a reaction, to speed up dissolving. Because here we're not doing a reaction, we are dissolving it in water. So to speed up the dissolving, we are breaking it down into smaller pieces. Name an item of apparatus that can be used to heat the water. So it's very easy to heat the water. We always use Bunsen burner. Name the apparatus labeled A. Now what is apparatus A? This one, this is apparatus A, which is a filter funnel. It is a filter funnel. Then describe what a student must do after step 3 to obtain dry crystals of pure sodium chloride. So after step 3, we will get a solution of sodium chloride in a filtrate. So when we have sodium chloride in a filtrate, what can we do to the filtrate to obtain pure crystals? Obviously, we will do crystallization. So we will write the steps of crystallization in this answer. So what we'll do? First of all, we'll heat the filtrate to evaporate the water until crystallization point. So we have to heat the filtrate until crystallization point because we don't want our water of crystallization to be lost. The next point will be that we'll let it cool. After that, when the crystals are formed, we will filter the crystal mixture, wash the residue with distilled water and dry. So these are the steps of crystallization that we'll perform. We'll first heat the filtrate to evaporate the water until crystallization point is reached. Then we will let that mixture cool down when it has small amount of water in it, still present in it. Then we'll filter the mixture. We'll get the crystals in the residue on the filter paper. We'll wash the residue with distilled water and then we can dry them in an oven or in the folds of filter paper. Then we have the next question, number 2. Student investigates the rate. Rate means speed. A student is investigating the speed at which hydrogen gas is made when magnesium ribbon reacts with dilute ethanoic acid. So here we are reacting an acid with a metal. And when we react an acid and a metal, we will get salt plus hydrogen gas. So here, the hydrogen gas is produced and a student investigates the rate of formation of hydrogen gas. This is the experiment. Student does 2 experiments. to find out the rate of the two experiments and which one will be faster, which one will be slower. So this is the apparatus. Here in the flask, student is using ethanoic acid. Conical flask, there's a bung, delivery tube, and through the delivery tube, the hydrogen gas enters into the measuring cylinder. Hydrogen gas collects at the top and the water level comes down. Experiment 1, use a measuring cylinder to pour 50 centimeter cube of ethanoic acid. Use a thermometer to measure the initial temperature. Set the apparatus, ensuring the inverted measuring cylinder is full of water first. Remove the bung from the conical flask. Ensure the delivery tube remains in the measuring cylinder. Add a coil of magnesium. So we will remove the bung, add the magnesium coil, immediately put the bung back again to prevent the loss or to prevent the escape of hydrogen gas produced. We will put the magnesium ribbon and immediately put the bung at the top of the flask. If the magnesium sticks to the side of the flask, gently shake the flask so that it is washed off to the side. Measure the volume of gas collected. So this gas hydrogen, we will collect it every 15 seconds for 150 seconds. Use thermometer to measure the final temperature. Rinse out the conical flask. Experiment 2, repeat experiment 1, but warm the acid by about 15 degrees Celsius. So what was the temperature before? The initial temperature. We have to warm the acid by 15 degrees Celsius this time and repeat the same experiment using same quantities of everything. Okay, now use the thermometer diagram to complete table 2.1. In this one, experiment 1, we have to read the initial temperature of the thermometer and the final temperature of the thermometer. Then we will take the average temperature. So the first temperature is, we'll start reading from the bottom as it's a thermometer. So 20, 21, 22, and it is 22.5. The final temperature is 25, 26, 26.5. Here, the initial temperature of experiment 2 is 35, 39.0. It's 39.0. And here, 40.0. Now we'll take the average. To take the average, we will add the two things. We'll add 2.5 and 26.5 and divide them both by the number of quantities. So we have two numbers over here, two temperatures, so we'll divide it by 2. That's how we take the average. We add the two things, add the substances, divided by the total number. And here also, we'll do 39.0 plus 40.0 divided by 2. That's how we take the average. For the first one, the answer comes out to be 24.5. And for the second one, the answer is 39.5. Then we will measure the volume of gas collected in experiment 2. Now for the experiment 1, it's already here, which is written. For experiment 1, the gas which is collected at these time intervals, so at 15 minutes, at 15 seconds, this is the time. This is the volume at 30. This is the volume at 45, volume at 60, 75, 90. So we have the volume obtained in experiment 1. Now we have to note down the volume obtained in experiment 2. So let's do it. We will read from the top because it is inverted measuring cylinder. So 10, 20, and this one will be 21. The next one will be 33. This is 45. This one, 54, 62, 68, 75, 80, 84, and 88. These are the volume of the gas collected in experiment 2. Let's move on. Now, we have to plot the graph and we have to draw the lines of best fit. Now, as it is a rate of reaction, so the rate, in the rate question, we always get the curves. So we have to draw the curves of best fit over here. Okay, let's draw. volume of gas collected. And we have to draw for both experiments, experiment 1 and experiment 2 both. The first one, time taken, the scale is already here. And for the gas collected, we have to find it out. So for the time taken, first of all, we mark for the time taken. It's 15, and every 15 seconds, after every 15 seconds, it's still 150. So we'll first mark it over here. It's 10. And here we got 15. Here we get 30. Then we have 45. Then we have 60. Then 70, 75. Then 90. Then 115. After 90, we have 105, then 120. 105, it will be somewhere here, 105. Then we have 120, then 135 here, 135, and then we have 150. So these are the timings. These are the time in seconds. And now we'll plot the graph for experiment 1 and 2 both. First of all, for 15 seconds, we have 12 and 21. Okay, let's make a scale first. So it is going till 62, and this one is going till 88. So I guess we'll take 20, 40, 60, 80, and 100. So we'll take this scale. For the experiment 1, it's 12 and 21. Experiment 1 is 12, experiment 2, 21. 12 and 21. So let's draw. For the first one, it's 10 and 12. Somewhere here, 12 and 21. It's 22 and 21 should be here. Then for the next one, for the 30 seconds experiment, it's 22 and 33. So for this, it's 22, 22, and 33. 30, 32, 33. For 45 seconds, we have 31 and 45. For 45 seconds, it's 31, 31, and 40, 45. For 60 seconds, we have 37 and 54. 37, 32, 37, and 54. 54, there you go. Then at 75 seconds, we have 43 and 62. 43 and 62. Next, at 90 seconds, 48 and 68. 48, 48, and 68. Then at 105, 52 and 75. 52 and 75. At 120 seconds, the volume is 56 and 80. 56 and 80. Here at 135, 59 and 84. We have 59 and 84. At 150 seconds, we have 62 and 88. 62 and 88. Here you go. So we got a graph like this. Now we have to draw the line of best fit. Now in this one, in the rate of reaction, we actually get a curve. So, but here we'll draw the line. Let's see. We have to draw the lines of best fit. With the scale. But here I'm just drawing randomly. You can use a scale to plot them. Okay. Okay. The points which are up and down, you have to leave them. Okay, like this, just draw it with a scale. Okay, so something like this you will get. Okay, and then you have to label them also, because this line is for experiment 1. This is for experiment 1. And the second line is for experiment 2. Label them properly. After that, the question is, deduce the volume of gas collected between 20 seconds and 40 seconds in experiment 1. Show clearly how you worked out your answer. No. Now, the reading between the gas collected between 20 seconds and 40 seconds here at 20 and 40 seconds. Deduce the volume of the gas. Now, at 20 seconds, we will just extend it upwards. Here for 20, extend it upwards. And for 40 also, between 20 to 40 seconds. And here, in 20 seconds, we are getting almost, this is 38. And here, at 40, oh, sorry, we have to do it for experiment 1. I did it for experiment 2. So we'll do for experiment 1, we'll leave till here. And this is coming almost 18. For experiment, for 40, we'll extend it upwards here. And then we'll go back, extend it backwards, and it's coming almost 30. So the gas collected, the volume of the gas collected between 20 and 40 seconds, it's 30 minus 18. So what we'll do, 30 minus 18. And then we'll write that between these, what gas we are getting. So 30 minus 18, Let's do it. 30 minus 18, it's 12 centimeter. So you have to work out very clearly. First, work it out on the graph like this and write the answers over here, like this 18 and 30. After that, write on the paper that you are doing 30 minus 18 to get the answer. And the answer is 12. Show it very clearly. The next question, use figure 2.2 to explain which experiment has the faster rate of reaction. Experiment with the faster rate and explanation. Now, as you can see in the graph, the one which is steeper has the faster rate. And here, the steeper graph is of experiment 2. So it means that experiment 2 has the faster rate. So here, which experiment has the faster rate? Experiment 2. And the explanation will be because the line is steeper. During experiment 1, the temperature of the mixture in the conical flask changed. State how this change in temperature affects the rate of reaction. So the temperature in the conical flask increases, as we can see here. We noted down the temperature, and in experiment 1, previously it was 22.5 and now it is 26.5. So it has increased. So if the temperature increases, how it affects the rate of the reaction? The rate of reaction also increases. Describe how the apparatus could be altered to minimize the change in temperature. Now, how this apparatus can be changed to minimize the change in temperature? So, we can place the flask in a water bath. So, if we place the flask in the water bath, we can minimize the temperature change. So, we should place the flask in a water bath. So, when we place the flask, see here, as we can see in the diagram, the flask is completely open. So the temperature can be increased or decreased. The temperature can be lost, the heat can be lost or gained because of this, because it's free. Now, if we put it in a water bath, this means that the water will absorb the heat, some of the heat, and the temperature loss or temperature gain will be avoided. It wouldn't be too much high, the temperature change. So the temperature change can be reduced by placing it in a water bath at the start of the reaction. The temperature will be maintained to maintain the temperature. So we'll place the flask in a water bath. Next one is some gas escapes in a short time between adding magnesium ribbon, the conical flask, and putting the bung back into the conical flask. So to do this, some of the gas escapes, as I told you before, that when we add magnesium, we have to put the bung back very quickly to avoid the escape of hydrogen gas. But what if it does? Explain how the apparatus could be altered so that no gas escapes and the results of the experiment are more accurate. You may draw a diagram to help your answer. Now for this one, there is one way that we should keep the acid and magnesium separate at the starting of the reaction and while having a bung. Means the magnesium should be inside the flask while having the bung on. So here, the proper way is that we should have acid in the flask. This is ethanoic acid. So we have ethanoic acid in the flask and we will use a thread, and with a thread there will be a test tube inside, and the test tube has magnesium ribbon inside it. It has a magnesium ribbon. And then we have the rest of the setup. Like we have this delivery tube, and the delivery tube is going into the measuring cylinder. Inverted measuring cylinder, and it is all placed in a water bath. So when we want to start the experiment, we can pull this thread the magnesium containing test tube will fall into the ethanoic acid and they start reacting. Or we can also do that, we can tilt the flask a little bit so that the ethanoic acid will start reacting with magnesium inside. We can pull the thread, tilt the conical flask, and the two things will be reacted. That's how we can avoid the escape of the gas, because the bung is on. Bung is already placed. No gas will lose. So what we can use, we can suspend the magnesium ribbon on the acid in the flask by using a test tube with a thread. Okay, and the second point will be that for the reaction, tip the flask. Tipping the flask means tilting the flask. So we can tilt the flask a little bit and the acid will start reacting with magnesium. The word which is used here is tip. You have to use the word tipping the flask. We use the word tip. Describe one other way in which the results of the experiment 1 and experiment 2 should be made more accurate. Now, how can we make it more accurate? First of all, by taking the reading again and repeating the experiment. And the second thing is using burette instead of measuring cylinder. Burette instead of measuring cylinder, or by repeating the experiment. It can be any answer, either way. Then sketch on the figure 2.2 the graph you would expect if experiment 2 is repeated using ethanoic acid with higher concentration. So we have to draw the line which indicates the experiment 2 when it is repeated with higher concentration of ethanoic acid. Obviously, the rate will be more, the line will be steeper. We'll draw the line like this, like it should start from 0. It will start from 0 and it will go above the experiment 2 line, because obviously the rate will be higher. We are doing it at more concentration of ethanoic acid, so the rate will be higher. Okay, and you will label it as X. This is X line. Okay, and this question is complete. We'll do the rest of the questions in the next video.